this next section, there's no crazy theme. Couldn't think of a nice picture to put in the background, so I put this picture of a person skiing, and I titled this "Other Helpful Things." So there's something that just didn't fit into my other talks that I wanted to talk about here, which is significance. What does statistical significance typically mean? What is that p-value? When someone presents data, it might look something like this, right? It's just a bar graph, and there are some error bars, and then there are these lines that basically go in between them with stars on top of them. And that's typically common, very typical. And sometimes they say NS, sometimes they have double stars, whatever. So that's companies saying things are statistically significant, right? And I think everyone knows that. So what does that actually mean? Well, that actually refers to a p-value. And to talk about a p-value, instead of telling you how to calculate one, which is actually, it's not that hard to do. You can look up on Khan Academy or something how to do p-value calculations. But to talk about a p-value, I'll just give you conceptually what a p-value actually is. A p-value is typically when you're comparing two things. You're holding one as true, and you're testing how far your second thing that you're measuring is from that truth. So in this example here, there is a statistical significance line here with 2 stars between the competitor and us. And this is something that you might see quite frequently. So in this case, what you're doing is holding the competitor bar as true. And remember, we have to think in distributions. And so you think about all the possible outcomes that are in that competitor bar. And you and assuming that these are all true possible outcomes for the competitor, where does your data fit on this distribution? And that is how you calculate p-values, right? So if your data is multiple standard deviations away from the mean of the competitor's kind of possible outcome distribution, then you have a small p. And if you're much closer in standard deviations, then you have a large p. And you can think about the p-value as the percentage shaded over divided by the entire distribution itself. So I always get this question of, for the p-value, why wouldn't you want to compare all possible outcomes for your kind of bar versus a competitor bar? It's just not how a p-value is calculated. For p-value to work, you have to hold one thing as true, and that's what you would graph as a distribution. And you want to know where you fall on that graph, assuming that this distribution itself is true. So that's why you're comparing two things, and this is called the null hypothesis, if you want the technical term. And the p-value is just calculated by looking at where your area is here. The stars have very particular meanings, right? So no significance actually means that your p-value is greater than 0.05. So this is bigger than 5% of the area under the curve. 1 star means a p-value is under 0.05%, and this is kind of what's generally accepted as statistical significance if your p-value is under 0.05. 2 stars is 0.01, 3 stars is 0.001. I think I've seen up to 4 stars. I don't think I've ever seen 5 stars. But the reason why you can have smaller and smaller and smaller p-values is that if you think about this distribution of possible outcomes, the line doesn't actually go to the x-axis. It goes to infinity, smaller and smaller, right? So this is a theoretical distribution. All right, so presented p-values are almost always small, right? You almost always see stars and people saying, hey, we have statistical significance here. And when they're not, they're usually hidden in the supplemental data. So, we talked a lot about deconstructing everything. Make sure you deconstruct the data and how these things were evaluated. And, these two numbers might be statistically significant, but maybe there are other important factors underlying them that makes that statistical significance irrelevant. And that happens all the time. You have to look at data, and I'll present you with a checklist of how I look at data later. The other thing I wanted to mention is that significance doesn't actually imply relevance. I'm a ex-management consultant, so I have to put a 2x2 matrix on here somewhere, right? So this is my 1 2x2 for the entire session and 3 sessions even. On the y-axis, you have significance, so decreasing p-value as you go up. And then you have effect size on the bottom, which is basically the distance between the peaks of whatever you're measuring. So remember, thinking in distributions, everything's a distribution. Your significance might be high if you have very little overlap between these two distributions. But because the peaks are so close to each other, the effect size might be small. Where you really want to be, as with all 2x2s that consultants show, is in this top right quadrant where you have good separation between the peaks and there's no minimal overlap between the two distributions. Sometimes you can have good distance between the peaks, but too much of a overlap, and thus you don't have statistical significance. This is something that you see quite frequently in the prospective data sets, and that's what I was talking about before. Like you see an effect size, but you can't actually call it significant in the difference because the shape of these distributions might actually change to be a tighter peak if you add more data. But with the amount of data you've collected, they are wide like this. There's too much overlap, and you can't actually say that there's a statistically significant difference, even though you see a nice effect size difference. Really, everything outside of that top right quadrant is meh. Like, who cares? And I mentioned this when talking about banana bio, right? The banana factor adds a nice 3% bump to the RNA itself to create a combined curve that has an AUC of 0.97. That 3% might be statistically significant, but I mean, seriously, who cares? It's 3%, right? It doesn't make a difference. This really, this reminds me of something that I see quite often in the winter. Well, maybe not this year or coming years, because I heard it's going to be dry. But when you go to Tahoe and you ski, if there are skiers in the audience, you see this bumper sticker a lot at Lake Tahoe. Nobody cares at Utelli. Those who don't know what telemark skiing is like, the type of skis that kind of go like this. So the boots detach from the actual skis, and you look cool, I guess. I don't know. I don't telemark ski, but it's the same thing. Nobody cares that Utelli. Nobody cares that it's statistically significant. What really you care about is the effect size coupled with the significance. You have to have both. I promised some examples of data and things that I see that try to trick me up quite frequently. These are 3 different types of data that I think you might typically see. And here, what you want to do is look for effect size as well as statistical significance. I really hate data presented like this and this, because the different colors, the density, the shapes, etc. It makes it seem like, yeah, you could tell a difference between these 5 groups, right? I mean, this is just a point, and this is down here in the gray, and it's more like a top, and then these are lengthened Hershey Kisses, and they all have different colors. I'm like, okay, great, the company can tell a difference between each of them. Same with this, right? Like, I mean, you see these types of graphs all the time. So a company comes in, they say that they took the sample data set, and using the whatever metrics that they're using in their fancy algorithms, they show that if you look at how a doctor defined different groups, for example, healthy versus mild disease versus severe disease, you can clearly see a difference between these 3 groups using whatever biomarkers that are special to you. And what they want you to see is something like this. Well, that's not usually what the data actually shows. So in the case of the first example, if I had to draw things out, not to scale, this is what I would think things look like when I think in distributions, right? Most of the data points actually overlap. And so most of these distributions overlap. And if you try to distinguish between each of these types, I mean, it's impossible, right? I mean, it's basically impossible. So something that seems beautiful and laid out and seems like a good data set here, it's just a visual trick of the eye. If you try to lay it out in a different way, then it probably looks like this. And if it looks like this, you can't really tell anything. Everything overlaps with each other. It's actually quite similar with this grouping 1, 2, 3. I mean, maybe this is mild, moderate, severe. I mean, who knows, what have you. Companies will have lots of different things that they're looking for in stratifying. But if you actually graph out the distributions, maybe you can get some separation between the blue and the red, but I would say it's impossible to really separate out, these groupings from either groups. In this particular case, like a column, which I'm not going to zoom in here because it doesn't really matter. A column is one patient, and so you're looking at, let's say, 300 patients across the entire length here, 100 per group. If I took any given column here, I wouldn't be able to tell if it came from group 2 or group 3, or if it came, from its own grouping, right? Because there's probably too much overlap. This is a way that people try to trick you up. Please don't be fooled. Uncouple the data that they're showing you, and then recouple it back into a different type of graph that makes more sense. And as I kind of am an advocate for thinking distributions. This one's a trick question here. Like I'm sure you'll see this data quite a lot. This is something known as a Kaplan-Meier curve. And it usually shows survival of something, whether it's humans or mice or what have you. On the y-axis, you have percent surviving, and then on the x-axis, you have time, whether it's weeks or months. And given the number of cancer companies out there, this is quite frequently used for cancer. Well, these two types of lines don't actually, it's hard to think of them as overlapping distributions. So here I think about it more as separate distribution curves. What do they look like, and what are similar between the two distributions? For example, as you step to the right and time goes by, more and more people die. And so this survival rate that's graphed on the y-axis, the way that you would read this kind of curve and say there's a difference and looking for the effect size, you draw a line through the 50% survival, which is the median, right? More people, just as many people are alive at this point as have died. And then you look at what the time is. And here there's a big difference between the two times. But if you go out towards the end, there's not that much of a difference between the people who died in the blue graph and the people who died in the green graph. So what are the similarities? And is there anything you can do with what the distribution curves might look like to note that? This type of data can be presented in many ways, and just be wary. Usually it's a control population in the blue. So like you give no drug to mice and they die quickly, and then you give drug to mice and they live for a longer period of time on average. That could be the case. There's a lot of companies that I've seen recently where it's the opposite. They're taking retrospective data of patients that have died of some sort of cancer, let's say breast cancer. And they say that if we picked the right patient population using our fancy algorithms, then you get this green curve and people would have survived a lot longer because you only gave drugs to those who actually needed it or where the drug actually worked. That gets really tricky. You have to figure out how to unpack that and figure out who they're subtracting from the blue curve to make the green curve. And they can, you can get kind of tripped up on that. So I would say if that's a type of graph that you see, then make sure you really dig into what the curves are and what's been subtracted to move one to the right. Okay, I'm going to stop with data and points there and go into something more practical. So I was asked to provide a checklist. Here is a checklist in a semi-order. I'd say that this is not necessarily the order that you have to go through, but I think of things in this order when I get started with technical diligence to reduce the amount of work that I have to do. So I start by dissecting the key data from the pitch, because a company will almost always show you their absolute best crown jewel in the pitch. Everything else gets cut into a technical deck or a follow-up meeting, etc. Right? So if you can understand what the key data is and validate that it's good, then that's interesting, and you can move on. Second thing I like to do is asking myself if things make sense. So if you understand what the key data is, does that actually make sense in the market that they're trying to play? I talked about the right sample for the right cancer population. Is that true here? Before running through all the different types of data that a company might provide you in their data room, it's nice to take a step and just think, does it make sense? And usually you're smart enough to know if something feels wrong. Then I would catalog data into a Rumsfeld matrix, and it's not exactly like this. And if you don't know what this is, it's just kind of the known knowns, known unknowns, etc. And that way I can prioritize what type of data I'm looking at and what type of data I need to ask for. Right? In a data room, there's going to be a lot of unknown knowns, things that the company knows that I don't know. And in the data room, there's probably not going to be some things that I want to know that the company may or may not know, and you have to ask for it. So cataloging things and prioritizing makes a lot of sense and helps you to do data diligence in a very systematic way. Then I want to make sure I understand experimental methods for any type of data that I feel like is key. So we mentioned before, there's a lot of biases that might be hidden in different techniques. So if someone says, I've collected RNA samples, how did you do that? Right? How did you actually draw the blood from the patients? How was the blood stored? What types of techniques were used to extract the RNA? Were things depleted or were things enriched? These are all things that you need to know and can add different types of biases to data. Once I understand experimental methods, that's when I go broad and look at the landscape of science outside of the company, right? This is when you prioritize and read related papers. I'll talk in the next slide about how to actually read papers, or at least what I do. And then once that's all done, I talk to people who know more than I do. And this is a step you can't skip, but I put it at the end for a reason. I mean, it's easy to try to ask someone at the very beginning, someone who knows more about the space than you do, what their opinions might be. But I like to leave things, if not towards the end, after I'm in the middle of diligence, so that I understand enough about the problem and the components of the system, so that I'm not, wasting anyone's time with rudimentary stuff. I can ask the right questions and understand the answers that are given back, especially when, a lot of times you don't have that much. You have a limited amount of time to talk to these people who know more than you do about certain things. Okay, so that's my checklist. I'll go into how I read journal articles, which at the end of the day is a lot of times not reading journal articles. I start with the title and abstract. If that's interesting enough and I feel like it's relevant to what I'm looking at, then I dive into the actual figures. I don't read the text. Because the data is usually, the crown jewel again of a paper. And if the data makes sense and looks good, then I would move on to the methods to make sure that I agree with how they generated the data. And don't, just because it's a fantastic peer-reviewed journal like Cell, that the methods are perfect. There's a lot of biases that you can find in methods a lot of times. But if I don't care about the title or the abstract, then I don't have to do any of the other stuff. Same here. If I don't like the figures, I don't have to do any of the other stuff. Then I go to the methods, and if the methods check out, then I look at the supplemental data, which could be 2 or 3 times as much data as actually presented in the figure. A lot of times it's not the most interesting stuff. It's a lot of controls, but it helps lend credibility to the stuff that they're presenting here and helps you build confidence in that. Usually by this point, I'm not, I feel like I have enough from the paper, and they don't actually read the text of the paper itself. And I would recommend that if everything checks out, then you can read the paper, or you don't have to. A lot of times the authors pontificate on things in the actual text, and it's nice to get their thoughts, and it's also nice not to have their biases in your mind in just evaluating the data. Actually, Alex suggested, he's a scientist by training, that if you are an expert in the field and you have a hypothesis, it's not a bad idea to come into a paper having your own hypothesis and seeing if the paper validates your hypothesis. So not a bad thing. I'm probably not as smart as Alex, and a lot of times when I'm reading these papers, I don't have a hypothesis. I'm trying to learn new things, and I just don't know enough. But if you can, then that's an absolutely good thing that you should do. And I'm sure there's a lot of scientists probably attending this talk, so that's probably what you should do. I'll end. These are the 2 books I mentioned. I think these are absolutely required reading for anybody, especially in the investment world. This is published in 1954, still very relevant today. This Thinking in Bets really helped set my mindset to probability thinking and risk stratification versus thinking in absolutes, and it goes well with my thinking in distributions. If you want some practice reading cool journals, I'd recommend kind of these sets of journals. I don't like paywalls. There's ways to get around paywalls. I'm not suggesting that you do, but you can. eLife is open access, and bioRxiv obviously is all stuff that's preprints, so that's all open access as well. If you want to look at really good data, a lot of times, Cell Press requires their articles to have an excess amount of data before they'll publish anything. And PNAS, I think, is super underrated. They have lots of really cool scientific articles, not just in biology, science, in like physics and chemistry and et cetera. And I would recommend reading through that.